Hello. So now we are going to look at the frequency dependence of the real and imaginary parts of the refractive index. I have simply borrowed these two expressions from my previous lecture. You can clearly see that what we are discussing now or focusing now is on this dispersive aspect, that is the frequency dependence of these quantities. If you look at both the expressions, they share a common denominator. You can clearly see where you see that the real part as well as the imaginary part has this omega naught minus omega whole square and plus beta square, right? This is a common denominator. Clearly, there is dramatic change in the frequency dependence when omega equals to omega naught because the denominator becomes the smallest and hence the response becomes the largest. We will of course look at both these quantities separately. So let me first begin with the imaginary part uh, uh, of the refractive index. So clearly you see I have plotted here the frequency dependence, and what I'm plotting on the x-axis is basically omega minus omega naught divided by beta, right? And you can clearly see that beta is my natural scale with which I rescale my frequency differences. So let me again remind you, omega naught is the atomic resonance frequency, that's a natural frequency, and omega is the drive or the incoming frequency that is driving this oscillator. So the resonance condition is of course when omega equal to omega naught. So you can clearly see that at resonance, you see that I get a peak. So this what I'm plotting here is Ni, the imaginary part of omega. At omega equal to omega naught, which is 0, I get a peak because the denominator goes down. And you see that as I go away from the resonance, the frequency dependence is 1 over omega square, essentially, far from beta. This quantity, you see that it takes a maximum value where apart from this prefactor, which I will not at the moment worry about, imagine this prefactor is a constant. The maximum value it takes is actually 1 over beta. And you can clearly see that at, at omega naught minus omega, if this quantity is equal to beta, right? In that case, you will see that the denominator essentially provides a factor of 2. That is, my 1 by beta would come down to half of its value at this quantity where omega minus omega naught is actually beta. So this is what is 1. So you see that the width of this resonance is actually twice beta. So twice beta is what we also call as full width at half maxima, is a acronym that we use commonly. So 2 beta now forms the width of this resonance. That beta was a measure of the dissipation in the system, and it is precisely beta that is governing how strong the resonance is, in the sense that if beta is small, the resonance is going to be higher and sharper, whereas as beta becomes large, the resonant response comes down. Not just that, the width of the response also increases. And the measure of the width of the response is essentially beta, right? So this is I mean, this is clearly, the resonant feature that we see all around us. For example, the lot of the color in nature is because of selective absorption, and these absorptions are happening at specific frequencies. But this is a very generic form of a line shape. I'll come back to the imaginary part a little later and talk about this distribution that we have, that is this particular form for the line shape that we have, but that is slightly later. Okay. Now let us look at the real part of the refractive index. At omega equal to omega naught, you see that suddenly this factor that is uh, that is highly dispersive or highly dependent on frequency. actually becomes irrelevant at omega equal to omega naught, right? So this actually contributes to zero, and what we get is a refractive index which is just 1. So again, I'm plotting the real part. You see that at omega equal to omega naught, so the x scales are exactly the same, you know, these scales are the same. So this is indeed omega equal to omega naught. At this point, I am marking this as 1, right? And these are quantities above and below 1. And you see that my at omega equal to omega naught, it goes to 1. And as you go away from this, so you will see that around omega naught, the slope of this quantity is actually negative, right? Because dn over d omega will give me a negative coefficient. And that is indeed true. That is captured here. Dn over d omega will give me something negative. So this is my real part of the refractive index. And you see in this region around the resonance, right? dn real by d omega is negative. And as you go away from this region, right, that is when you see that the denominator actually becomes significant. For omega naught minus omega larger than beta, is the prefactor at the bottom that becomes dominant. And you see now the refractive index, the in this region as well as in this region, my dnr over d omega is actually positive, right? This region where system is positive, that is away from resonance, right? On either side of the resonance, this region is what is called as normal dispersion. So the normal dispersion essentially is the region where refractive index, the absorption itself is negligible, if you like, right? This is where we make, for example, prisms, wherein you see that the refractive index actually increases with frequency. You can clearly see that because dn over d omega is positive, which implies that uh, n for red, right, which has a frequency which is lower and is going to be less than the n for blue, right? Because dn over d omega is positive. So this is where prisms will bend blue light more than the red light, and hence this region, which is away from the resonance, where dn over d omega is positive, this region is called the region of normal dispersion. Whereas if you look at the the region which is around the resonance, right? This is the region where dn over d omega is negative, and this region is called anomalous dispersion. This region corresponds to anomalous dispersion. Now, remember, the anomalous dispersion region is actually coming in with significant absorption. That would mean if I try to make a medium which has got uh, which will reverse the colors, that is within the anomalous region, imagine the red light would travel faster than the blue light, for example. In that situation, if you want to reverse it, it will also consequently suffer large absorption. So this absorption and anomalous dispersion come together, right? So if you so typically you will have transparent material media which will show normal dispersion. In summary, the normal dispersion is always accompanied with sort of transparency, whereas if you are having absorption in that situation, you will invariably suffer anomalous dispersion. So this anomalous dispersion and absorption will go hand in hand. By the way, this is what is also governed or dictated by something called the Kramer-Kronig relationships, which I had mentioned very early on. which essentially is a relationship uh, uh, arrived out of purely ensuring causality, and this relationship actually relates the real and imaginary parts of refractive index, and this is that relationship that we have captured here. You can clearly see where does it make a difference. For example, you have derived in the assignment the notion of a group velocity, right? Remember, the group velocity I defined as d omega over dk in comparison to the phase velocity. Remember, v phase was simply omega over k, right? So if you look at group velocity, you see that dn over d omega over dk can be rewritten in this form, where it is c by n plus omega times dn over d omega, right? And this is precisely here when we talk about n, that is indeed the real part of the refractive index, right? So you see that depending on the sign of dn over d omega, which is anomalous or normal, you see that the group velocity can be larger or smaller than c. That is why I mentioned early on that even if you have light which is propagating faster than the speed of light, it doesn't necessarily mean that you're violating causality, or you, for that matter, you're violating any of the principles of the special relativity theory, right? Because what you have here is essentially dispersion, which can be tailored, or played around with, so as to achieve variety of things, including getting a group velocity which could be smaller, larger, and so on and so forth. So people have done very interesting experiments, by the way, which I should mention, that rather than creating an absorption peak, for example, if you um, realize a gain peak like that in a laser where you're doing pumping and this is absorption turned into gain, right? In that case, you see that the sign of the corresponding refractive index in that region from anomalous becomes normal. And you see, so one can basically play around with these line shapes. Of course, you'll see that the real and imaginary part themselves cannot be um, torn apart, but one dictates the other and so on because of the Kramer-Kronig relationship, and one can actually engineer the dispersion to achieve variety of things, right? Um, Remember, to derive this expression, we have used this fact that my dispersion relation, that is my k, is omega by c times the refractive index n of omega. You recall that this was our definition. So before I go ahead, I want to talk about this line shape function. So you see that my absorption coefficient, as I had indicated earlier, right, which is a function of nu, can be written down in this form. It's n e square 4 epsilon naught m c times delta nu naught by pi by nu minus nu naught whole square plus delta nu naught whole square. So what I have done is the following transformations, that my nu naught is basically omega naught divided by 2 pi. My nu is simply omega by 2 pi, right? So I'm talking about in terms of linear frequency, and my delta nu naught is basically the rescaled value of beta in terms of 2 pi. Beta over 2 pi, I call it as that. So why am I doing this is because this particular object, right? This particular object is known as the Lorentzian. So L of nu is known as the Lorentzian, and it is essentially this object, delta nu naught by pi, nu minus nu naught whole square plus delta nu naught square, right? Um, This is called a line shape function or the Lorentzian line shape function. The interesting thing would be that if I integrate from 0 to infinity, right, this L of nu d nu, I would essentially get a 1. It's normalized, right? And not just that, the maximum value. So I'm just writing down a few characteristics of the Lorentzian. The L nu max, right? This this happens at essentially nu equal to nu naught, and you see that it takes a value of 1 over pi delta nu naught, right? And you see that the at nu naught plus minus delta nu naught, what you get is half of the maximum value, which is L at nu naught. Right? You can check that out. So at nu plus minus delta nu naught, you see that this factor is precisely, from the maximum value where the denominator was delta nu naught square. Now the denominator becomes twice delta nu naught square, and hence this implies that twice delta nu naught is my full width at half maximum. Right? This is just to talk about this uh, line shape function, which I mentioned that I will introduce. And it's so this is a line shape function. For example, if you have an atom wherein the governing decay is spontaneous emission, for example, then you see that it's a Lorentzian line shape that we get. Um, and even for other mechanisms of decay, for example collisional broadening, also you get Lorentzian line shape. So I'll come to the line shapes slightly later, but this is just to give you uh, some idea about how to think of this particular aspect that characterizes the kind of absorption that you would get in the spectral domain, right? So you get a maximum absorption, and the absorption actually, the line shape actually goes like 1 over frequency square as you go away from it. It is not an exponential decay like in a Gaussian. It has got a very long tail, which only goes like 1 over the frequency square. So now I'm going to talk about the quantum mechanical aspect of this atom. We have only discussed it classically, but in quantum mechanics, what you get a little more detail and a little more complication. So what happens is, for example, in the hydrogen atom, what you have is the proton, okay, and you have the electron. The binding force between them is the Coulomb force. Quantum mechanics actually tells you that what you get is basically there are only certain allowed states the electron can occupy around this around the nucleus, and that is governed by some quantum numbers. So that is, for example, if the electron is in a particular state within the atom, it can be described by quantum numbers. We call it the principal quantum number n. Then there is a orbital quantum number L, okay, that talks about the orbital angular momentum of the atom. Then there's a magnetic quantum number m, right? And apart from this, there is also the spin quantum number. The so this principal quantum number n just varies from 1, 2, 3, and so on. These take integer values all the way to infinity, and you see that L, in contrast, so L can take values from 0 to 1, 2, and so on till n minus 1, right? And so every n, every quantum number n has got appropriate possibilities of the angular momentum. And then for every L, there are minus L plus 1 all the way to plus L, right? So there are 2L plus 1 states associated with every L. So you see that if you look at this, the number of states which are available is essentially I have to sum over uh, for a particular n, right? So number of states available is from L equal to 0 to n minus 1, and I have 2L plus 1 states in each, and this, by the way, you can check it out, comes out simply n square. And you see the electron itself carries a intrinsic angular momentum called the spin, and that gives us the fourth quantum number ms, which can essentially take the values of plus minus half. So the angular momentum has a value h cross by 2, plus h cross by 2, and minus h cross by 2, and hence what you get is essentially 2n square possible states associated with every quantum number n. Okay, so what you have is you have a hydrogen atom, you have the electron, and now the electron can occupy multiple of these states. Now, as you go down the periodic table, you see that the number of electrons increase, and the electrons need to be now filled in carefully from the lowest to the highest states. The principle required to fill up these electrons is essentially given by the something called the Pauli's exclusion principle. The Pauli's exclusion principle is fundamental to the structure that we see around us, and it is this that actually makes us look at material which looks like a solid, or liquid, and so on. And this Pauli's exclusion principle essentially states that no two electrons can have, these are these quantum labels. These are labels that label a particular electron. You cannot have a situation where all the labels for two electrons is exactly the same, right? That is, no two electrons can occupy exactly the same state, right? So given this constraint, one needs to now go ahead and fill up the possible states the electron can be, and that essentially which sort of in brief captures the structure of material media. Now let's say from atoms we want to go to molecules, right? So molecules in the simplest of scenario, let's look at the hydrogen molecule. You have a hydrogen atom, you have two hydrogen atoms, and you're putting them together. Now both of these hydrogen atom contains precisely one electron. Both of them, imagine they're in the ground state. And because they are spatially so far apart, they are distinguishable set of electrons. So as you bring these atoms together, the nuclei of these two atoms together, you see that the electrons and the nuclei are going to interact with the other. So you see that space in which the electrons are moving is common. And again, even though the original atoms are identical and the electrons occupy them were identical, when you put them together, they cannot occupy the same state. So this can be thought of pictorially. So let me just do that. What I am plotting is energies as a function of the interatomic distance. Let me call that R. And you see that in my energy scale, positive energies correspond to unbound system. That is, they are no longer together, whereas negative energies correspond to binding. When these atoms are reasonably far away, so you see that the energies are zero, right? And then as you come closer, you see that this is what would happen to one of the energy states, and there are two degenerate energies which now start splitting off, and this is the kind of character that you would get, right? So far away you have two degenerate energy states which correspond to these two individual distinct atoms. As you get them together, the Pauli's exclusion principle doesn't allow these two uh, now indistinguishable electrons to occupy the same state. So what nature does is to basically rescale the energies, or the states themselves become energetically distinct. So this is called as the anti-bonding state, right? You can clearly see that the energy corresponding to that is positive, and hence they are not binding ones, and this is called the bonding state. And so what would happen is that the electron now can actually occupy this binding state. And remember, there were two electrons. So for example, one could be a spin up, the other one could be spin down. And in that situation, I would have satisfied the Pauli's exclusion principle. And you see, the realignment of the spin will ensure that we are not violating that essential principle. This region where you find the minima of the bonding state is precisely the interatomic distance between the molecule. Could be of the order of an angstrom or so, right? This is right. So we are talking about 1 to 3 angstroms, uh, and so on in the scale. So um, this is how nature basically behaves, right? Now, rather than having, so now the one can talk about these two molecules themselves. So these, so the simplest model is that of a dumbbell, right? Because these molecules are now confined to remain uh, under the influence under the influence of the Coulomb interaction between the electrons uh, and the nuclei, which is keeping it all together. The fact that there is going to be a confinement at that scale is again going to lead to quantization. So apart from the electronic states that you have, now one can talk about vibrational degrees of freedom of this atom. So, there are very simple models that essentially capture, these various characteristics. So the electronic degree of freedom would correspond to energies in the in UV and visible. And then you have, the fact that you have put these two atoms together in a molecule. These can themselves have a vibrational degree of freedom about their natural bond length, right? So there is an equilibrium bond length, and one can oscillate about that. So one can have vibrational degrees of freedom. So this vibrational energy corresponds to essentially in the infrared, its energies are in that regime. Over and above that, you have the rotational degree of freedom. So now that the molecule is bound and vibrating, it can also rotate about its axis, uh, and the rotational degrees of freedom, the rotational energy regime is in the microwave. It's very important to realize that these three distinct regimes is what allows us, to consider some of the energetics and the dynamics of the what is happening in the molecule, with ease. Because if all of these energies were comparable, we would be in extremely sticky situation in terms of analysis of these various degrees of freedom. And this distinction is precisely occurring because of the large difference. So just take this, one can actually do a very simple calculation to support this. So the energy distinction is arising precisely due to the difference in the mass of the nucleus in comparison to mass of the electron. So the nucleus in the simplest scenario is, much, much larger than the mass of electron, and the governing force is Coulomb. It is this distinct difference in the masses of these two entities that is what creates this variety or the whole spectrum of energy scales that one talks about. It is important to understand these varieties of degrees of freedom. One of the most efficient bulk lasers is the carbon dioxide laser. It's a difference between vibration energy which is extracted as lasing radiation in a carbon dioxide laser. So it is these variety of um, accessible states that we can focus on and create situations for lasing to happen efficiently. Right. So from molecules, let us go to a little bit more complication, which is that of solids, right? So in solids, what happens rather than just having two atoms, or a few atoms, what you have is a Avogadro number of uh, atoms, 10 to the power 23 atoms, all aligned in a periodic fashion. So you see that each one of them would contribute, for example, the energy states. And now you would see that depending on the interatomic distance, if I'm thinking of, you know, if I'm thinking of energy states associated with atoms, the corresponding these energy states would split into, you know, bands, right? And these bands might be of, you know, so the number of energy states actually depend on the number of atoms which are there. And in all of these cases, I'm talking about, sort of 10 to the power of 23, Avogadro number of atoms, and you have these bands. And depending on the location and the interatomic distance within this periodic arrangement of solids, one can have these energies turning into bands and overlap between them. If there is a finite difference in the energy, so then these are the ones that form uh, insulators and semiconductors, right? If the energy is below 7 eV, we call them as, semiconductors, and above 7 eV, we consider them as insulators. And then you also have conductors wherein the bands overlap and so on and so forth. So you see this variety of structure that we get for n atoms. A simple way to look at it is when you have n atoms put together, you will split individual levels into n levels. And you see that the energy spread, right? For energy spread, the would actually now start depending on the interatomic distance, right? This is clear from the two atom scenario that we talked about here. Clearly, you see as you vary the interatomic distance, you see that the splitting in the bonding and the antibonding state depends on, where exactly you are placed. So you see that is precisely what is what I am conveying here. For the spread in the energy levels basically depends on the interatomic distance in such a periodic arrangement of n atoms. And there are variety of other solids. There are covalent solids, there are ionic solids, there are molecular solids that depend on van der Waals force of attraction. There are metallic solids which have got one, two, three electrons in the outermost uh, unfilled configuration. And so what happens is the electrons are being shared because they are free to travel in a band, and that is what causes conduction. And then one can think of impurities, imperfections, and all of these other details come into play as we talk about solid. So you see that is how extremely rich is this choice of material and the possibilities that we have. So we have solids, liquids, gases. You have a variety of solids with different behavior. Within the atom itself, there are different energy landscapes that one can access to make a laser. So all of this have to be put together to actually figure out a, a reasonable active medium for lasing.